We expected wonders. We found warnings. For most of human history, the stars were lights, not places. They looked fixed, pure, almost ceremonial. We could project gods onto them, stories onto them, navigation onto them, but not weather, geology, chemistry, catastrophe. The sky was a ceiling, not a neighborhood. Then we learned that stars are suns. And once that happened, another thought followed with almost unbearable force. If our sun has planets, then other stars must too. For a long time, that idea felt comforting. Maybe beyond the solar system there were other Earths waiting in the dark. Other blue worlds. Other familiar skies. Other climates mild enough for oceans, continents, storms, and life to take hold. Maybe the universe was full of second chances. Full of backups. Full of homes. But that is not what the data began to show us. What we found beyond the solar system was not a polite repetition of the architecture we know. We did not find a second Earth waiting patiently at the first doorstep beyond the sun. We found worlds that swing around their stars in days. Giant planets skimming stellar surfaces like trespassers in the fire. Rocky planets hot enough to carry oceans of magma. Skies full of poisonous gases, crushing pressure, metal vapor, silicate haze, and weather so violent that ordinary language sounds childish against it. We found planets with permanent day and permanent night. Worlds with no sunrise because one hemisphere never stops burning and the other never stops freezing. Systems packed so tightly that the planets seem less like a family and more like survivors in a traffic collapse. And out in the dark between stars, we found reason to suspect orphan worlds wandering without suns at all. This is the deeply disturbing truth. The universe beyond the solar system is not empty. It is crowded. But what crowds it is not reassurance. It is extremity. The frightening thing is not that alien worlds are rare. The frightening thing is that so many are built on rules that make our home look improbably gentle. We did not step outside the solar system and discover that Earth was ordinary. We stepped outside and discovered a catalog of cosmic bad neighborhoods. And the more clearly we look, the more disturbing the pattern becomes. Because this is not just a story about hostile planets. It is a story about expectation collapsing. About the meaning of normal breaking apart. About the possibility that the architecture that made life here possible may be narrower, stranger, and more contingent than we wanted to believe. Tonight, we are going to move carefully through that realization. Not through fantasy. Not through tabloid alien headlines. Not through exaggerated promises of life on every other rock. We are going to look at what astronomy has actually found beyond our system, the methods, the surprises, the atmospheres, the orbital weirdness, the fragile edge of habitability, and the unnerving possibility that the cosmos makes worlds far more easily than it makes homes. And by the end, the disturbing truth may not be that we are alone. It may be that a world like ours was never the universe's default setting at all. There is a kind of scientific discovery that adds new items to an inventory. A new moon. A new comet. A new galaxy. A new particle. Then there is a different kind of discovery, the kind that changes the meaning of the inventory itself. Exoplanets did that. The discovery of planets around other stars did not merely add more worlds to astronomy. It forced a re-evaluation of what a planetary system is allowed to be. Before exoplanets, the solar system served not just as an example, but as an unconscious template. There were rocky inner planets, gas giants farther out, roughly stable spacing, long orbital periods, and a kind of orderly architecture that felt so natural we mistook it for standard. Then other systems began to appear in the data. And they did not look like us. The first shock was not subtle. The first confirmed planet around a sun-like star, 51 Pegasi b, was a giant planet in a blisteringly close orbit. A hot Jupiter. A type of planet our own system does not have and classical expectations had not centered. It was as though the universe had responded to our first serious attempt at comparison by showing us not a cousin, but a provocation. Since then, the catalog has exploded. Thousands of confirmed exoplanets, thousands more candidates, and entire subcategories of worlds our solar system never built. Super-Earths. Mini-Neptunes. Ultra-short period planets. Puffy low-density worlds. Dense iron-rich remnants. Tidally locked terrestrial planets. Potential ocean worlds. Rogue planets. Compact resonant systems with multiple planets squeezed inside the orbital distance of Mercury. Atmospheres thick with exotic chemistry. Climate regimes with no earthly parallel. What emerged was not merely abundance. It was disobedience. The universe appears to be extraordinarily good at making planets. But it is not especially committed to making them in forms that flatter human expectations. This is the deeper reason exoplanets feel emotionally important. They did not just extend our map. They destabilized our sense of what counts as ordinary. And that has consequences. Because when people hear that there are countless worlds beyond the solar system, they often take it as good news for hope. More planets means more chances for life. More chances for Earth-like conditions. More chances that somewhere out there another biosphere, another intelligence, another familiar sky has assembled itself. Maybe. But the exoplanet revolution has taught a harsher lesson alongside that hope. Planet formation is prolific, but habitability may be fragile. Nature produces worlds easily. It may produce balanced worlds much less often. Finding many planets does not automatically mean finding many homes. That is why this documentary matters. We are not interested in fear for its own sake. We are interested in the way scientific reality can feel disturbing without becoming dishonest. Deeply disturbing does not have to mean monsters, invasions, or apocalyptic fantasies. Sometimes it means something simpler and more severe. It means the universe is under no obligation to make places where life, complexity, and long-term stability are easy. Beyond the solar system, what we found is not one terrifying object. It is a pattern. A pattern of extremity. A pattern of architecture so strange that our own celestial neighborhood begins to look less like the obvious outcome of planet formation and more like a special arrangement we were lucky enough to inherit. So we begin where this story truly begins, with the moment astronomy first realized that planets did not belong only to us. And with the shock that followed when the first alien systems refused to behave. For a long time, exoplanets were not absent from science because astronomers lacked imagination. They were absent because the task was cruel. Stars outshine their planets so brutally that trying to see a planet beside a star is like trying to photograph a firefly next to a lighthouse from thousands of kilometers away. Planets are small, dark, cold by comparison, and buried in glare. For much of modern astronomy, everyone suspected they existed. The problem was not belief. The problem was detection. This is why the discovery revolution feels, in retrospect, almost explosive. Once the first reliable techniques matured, the silence broke. The radial velocity method was one of the first great doors to open. Instead of trying to see the planet directly, astronomers measured the tiny wobble a planet induces in its star. A star does not sit perfectly still while its planets orbit. Both star and planet orbit a shared center of mass. If a planet is massive enough and close enough, the star's light shifts minutely as it moves toward and away from us. That shift can be measured spectroscopically. Then came the transit method, even more transformative at scale. If a planet passes in front of its star from our line of sight, it blocks a tiny fraction of the starlight. Monitor enough stars for long enough, and those periodic dips begin to reveal worlds. Kepler turned this into a planet-hunting machine. It did not simply discover exoplanets. It changed the statistical meaning of the galaxy. It showed that planets are not rare adornments. They are one of the common products of star formation. Other methods joined the effort. Gravitational microlensing, which uses gravity's bending of light to reveal planets at great distances. Direct imaging, difficult and selective but spectacular when it works. Timing variations and, more recently, astrometric refinements. Together these methods built a new planetary census. And what they found did something psychologically important. It ended our monopoly. The solar system was no longer the only example. That sounds obvious now. It was not obvious emotionally. For the first time in history, planets became part of the general furniture of the galaxy. The Milky Way was no longer just a city of stars. It was a city of systems. But the first discoveries did not soothe us with familiarity. They startled us with bias. The easiest planets to find in the early era were big ones close to their stars, because those produce strong signals. That selection effect mattered, and astronomers understood it. But even after accounting for bias, the first wave of exoplanets still landed with force. Giant planets were turning up where our solar system said they should not be. Systems seemed compressed, heated, dynamically restless. This was the first philosophical consequence of the exoplanet age. Planet was no longer a simple word. It was no longer shorthand for some variation on Earth, Mars, Jupiter, and Saturn. It expanded into a category vast enough to include states of matter, temperature, atmospheric chemistry, and orbital architecture that felt almost deliberately uninterested in our expectations. That shift matters because the imagination had quietly done something dangerous before the data arrived. It had assumed that other planetary systems probably meant other versions of ours. Once the discoveries came, that assumption cracked. The universe was not cloning the solar system. It was improvising far more aggressively. Kepler deepened the shock. By staring at one patch of sky and watching the brightness of stars, it revealed that small planets are common. Some stars host tightly packed systems. Some host multiple sub-Neptune-size bodies in configurations we do not see around the Sun. Statistical inference from Kepler changed everything. The galaxy likely contains hundreds of billions of planets. Planets are not cosmic rarities. They may outnumber stars. And still, abundance was not the comforting part. The comforting story would have been this: there are many planets, and many are likely to resemble Earth in stable, familiar ways. The real story is harsher. There are many planets, yes. But the range of planet types, orbital regimes, irradiation levels, atmospheric conditions, and system architectures is so broad that many planets tells you almost nothing about how many Earth-like worlds truly exist. The discovery revolution broke the old cosmic imagination because it forced a distinction we had not emotionally prepared for. Many worlds is not the same as many refuges. The galaxy may be rich in planets and poor in gentleness. That is the note we carry forward now, because once the detection era matured, a more uncomfortable question followed. If there are so many planetary systems, why does ours look the way it does? And more importantly, how unusual might it be? There is a danger in growing up inside one example. You stop noticing what makes it particular. For centuries, the solar system was not only home. It was the only planetary architecture we knew. Even after heliocentrism displaced Earth from the center, we still lived inside a kind of quiet exceptionalism. We had no real comparison set. Rocky planets inside. Gas giants outside. Nearly circular orbits. A wide habitable zone around a stable star. A large moon. Outer giants that may have shaped impact histories and orbital dynamics. A system spacious enough that the inner worlds were not crushed into days-long years or stripped under constant tidal punishment. This arrangement felt natural because familiarity is one of the most persuasive illusions in science. Exoplanets challenged that illusion. Now, to be careful, astronomers do not claim that the solar system is a miracle or a complete outlier. Nor do we yet have a perfectly unbiased census of all planetary architectures, because our detection methods still favor certain sizes and orbital distances. But even with those caveats, a pattern has emerged. Our system may not be the galactic default we once unconsciously assumed. One of the clearest clues is the prevalence of planet types we simply do not have. Super-Earths and mini-Neptunes appear to be common around other stars. Depending on exact definitions, these are worlds larger than Earth but smaller than Neptune, with a variety of possible compositions ranging from rocky to volatile-rich to gas-enveloped. Our solar system has no obvious representative of this class. We jump from Earth and Venus to Uranus and Neptune, with a broad missing middle. That gap may not be typical. Then there is orbital compactness. Many systems discovered by Kepler contain multiple planets orbiting close to their stars, sometimes with periods of only days or weeks, packed inside the distance between the Sun and Mercury. Our solar system, by contrast, is relatively spread out. Inner planets are not huddled against the Sun in a densely resonant chain. The architecture we call normal may be only one outcome among many. Jupiter adds another complication. Giant planets can reshape whole systems. Their migrations, resonances, and gravitational sculpting can stir or stabilize smaller worlds depending on the history. Some models suggest the early movements of our own giant planets helped determine the final arrangement of inner rocky worlds. That means the solar system's apparent calm may be the surviving product of a dynamical past that could easily have gone another way. And then there is habitability itself, which people tend to simplify into distance from the star. But habitability is architectural. It depends on stellar behavior, orbital stability, atmospheric retention, magnetic environment, geochemistry, long-term climate regulation, impact history, and often system-level interactions that can either protect or destabilize a planet over billions of years. The disturbing implication is not that Earth is impossible. It is that Earth-like persistence may depend on a chain of contingent conditions that many planetary systems do not satisfy. This is why the solar system begins to look less like a template and more like a successful arrangement among many failed or hostile possibilities. Not failed in the sense that no planets formed. Failed in the sense that planet formation is easy, while gentle long-duration surface conditions may be hard. There is something emotionally disorienting in realizing that our planetary neighborhood may be unusually polite. Jupiter stays far out. Mercury is not joined by a giant gas world skimming the Sun. Earth is not tidally locked. Venus teaches us how badly things can go, yes, but Earth endured. The outer system provides a buffer of ice giants and gas giants in orbits that are dramatic but not system-destroying. We often treat all this as background scenery. Exoplanets force us to reconsider. The architecture itself may be part of the miracle, or at least part of the contingency. And nothing shattered the old template more quickly than the first truly scandalous class of exoplanets. The planets that should not have been there at all. Hot Jupiters. If you wanted to disturb a solar system-trained astronomer in the 1990s, there was a simple way to do it. Put Jupiter next to the Sun. That, in essence, is what the first great exoplanet shock accomplished. A hot Jupiter is a gas giant orbiting extremely close to its star, often in periods of just a few days. These planets can be as massive as Jupiter or even more massive, yet they occupy regions where classical intuition, trained on our own system, had not placed giant planets. The first confirmed planet around a Sun-like star, 51 Pegasi b, announced itself with exactly this kind of affront to expectation. It is difficult to overstate how disruptive that was. Our own gas giants sit far from the Sun, beyond the frost line where volatile compounds could condense during formation. In older formation pictures, giant planets were expected to arise in the cold outer regions of protoplanetary disks. A Jupiter-sized world circling scorchingly close to its star seemed to violate the spirit of what many astronomers expected planetary systems to do. The eventual answer was not that giant planets formed comfortably in the furnace, but that planets move. Migration became unavoidable. A gas giant might form farther out, then interact with the disk or with other bodies and spiral inward. That realization was one of the first major lessons exoplanets forced onto theory. Planetary systems are not static blueprints. They are histories of movement, scattering, resonance, instability, and survival. Hot Jupiters therefore did more than introduce a new type of planet. They introduced a new mood. They made planetary systems feel dangerous. A migrating gas giant is not a passive neighbor. It can disrupt the material from which smaller rocky planets form. It can fling bodies outward, inward, or out of the system entirely. It can reshape the architecture of a young planetary family before anything like Earth has a stable chance to emerge. The presence of a hot Jupiter implies a past that may have been dynamically violent enough to sterilize or prevent entire categories of worlds. That is why hot Jupiters are emotionally important to this documentary. They are not only weird objects. They are evidence that normal is often built on survival after chaos. They tell us that beyond the solar system, there are planetary histories in which giant worlds do not politely stay in the suburbs. They charge inward like gravitational vandals. And what are these planets like? Hostile in ways that sound almost theatrical, but are entirely physical. Their atmospheres can be heated to thousands of degrees. Some are puffed up by stellar irradiation into bloated giants with low densities. Some may lose atmosphere under intense stellar bombardment. Their skies can contain vaporized minerals, titanium oxide, silicates, and molecular fragments that have no comfortable analog in Earth's climate. Their weather, driven by extreme day-night temperature contrasts, can involve supersonic winds redistributing heat around the planet. Some hot Jupiters are tidally locked, always showing the same face to their star. One hemisphere bakes under relentless radiation. The other, though still hot by human standards, can be radically different in chemistry and cloud formation. These are not worlds in the romantic sense. They are laboratories of excess. Scientifically, hot Jupiters became incredibly useful because their large sizes and close orbits make them easier to detect and characterize. Some of our earliest atmospheric spectra from exoplanets came from these worlds. So the first planets to shatter our expectations also became the first alien atmospheres we began to read. Philosophically, though, their importance is darker. They told us early that the universe does not share our mildness. It can build giant planets and place them in orbits that feel less like celestial design and more like aftermath. And once astronomers absorbed the lesson that planets migrate, systems rearrange, and giant worlds can end up in infernal proximity to stars, another shock followed. Not giant planets in impossible places this time. But classes of worlds our own system never made at all. One of the most revealing features of the exoplanet revolution is not a strange planet we discovered. It is a strange absence in our own system. When Kepler began to populate the galaxy statistically, a pattern emerged that was almost rude in its implications. Many stars seem to host planets in a size range our solar system conspicuously lacks. Bigger than Earth. Smaller than Neptune. Too large to be simple terrestrial twins, too small to be classical gas or ice giants. These worlds, broadly called super-Earths and mini-Neptunes, may be among the most common kinds of planets in the galaxy. And we have none. This is more than a cataloging curiosity. It suggests that the solar system may have sidestepped one of the universe's favorite outcomes. Now, these labels are broad and imperfect. Super-Earth does not mean better Earth. It often just means a planet more massive or larger than Earth, potentially rocky but not necessarily Earth-like in any habitability sense. Mini-Neptune refers to planets smaller than Neptune but with significant volatile or gaseous envelopes. The boundary between the two is not a sharp natural law but an area of ongoing study involving radius distributions, atmospheric loss, core mass, and formation history. Still, the overall point is clear: the galaxy is rich in planets occupying this missing middle. Why does that matter? Because it tells us our inventory of what a normal planetary system looks like was drawn from a non-representative sample of one. Some of these worlds may be rocky and massive, with extreme gravity and thick atmospheres. Some may be water-rich or volatile-rich. Some may have hydrogen-dominated envelopes that create pressures and temperatures hostile to surface life as we know it. Some may have begun as mini-Neptunes and then lost atmosphere under stellar irradiation, leaving behind stripped rocky cores. The diversity inside these categories is probably enormous. And that diversity is part of the disturbing truth. We often hear that Earth-sized planets are exciting because they are potentially habitable. That is fine as a search strategy. But the real exoplanet census suggests the galaxy is very comfortable building worlds in forms that are not quite Earth, not quite Neptune, and possibly bad at being hospitable in precisely the ways a casual optimist would prefer. Imagine a world several times Earth's mass, wrapped in a thick atmosphere, with immense surface pressure and temperatures that forbid liquid water surface conditions. Imagine another with a vast volatile layer over a high-pressure interior, where any ocean may be cut off from rock-water cycling by exotic ice phases under crushing depths. Imagine a planet large enough to hold a smothering envelope but small enough to feel, in headlines, temptingly Earth-adjacent. These are not impossible worlds. They may be common. That commonness is philosophically rough. It means the universe may have a strong tendency to produce planets near the life-friendly category without actually landing there. Worlds that gesture toward habitability in size, but fail in atmosphere. Worlds that resemble possibility from a distance and disappointment up close. And remember, our solar system avoided this middle-heavy architecture. Why? Planet formation models explore many possibilities: disk properties, migration histories, timing of giant planet formation, resonance shepherding, collisional evolution, atmospheric loss. We do not yet have one neat answer that makes the solar system's configuration inevitable. That uncertainty matters. It reinforces the sense that planetary systems are contingent historical outcomes, not clean copies from a universal template. There is another emotional effect here too. Super-Earths and mini-Neptunes remind us that familiar categories are parochial. The words rocky planet and gas giant once seemed like most of the story. Now they look like end members in a much broader continuum of planetary possibility. Nature is not dividing the galaxy into Earths and Jupiters for our convenience. It is experimenting. And once you accept that, another category becomes deeply unsettling. Not just worlds unlike ours, but worlds where even the basic rhythm of day and night may have broken down into permanent asymmetry. We live on a rotating planet with a moving line of dawn. That fact is so normal to us that it does not feel like architecture. Day becomes night. Night becomes day. Temperature rises and falls. Weather cycles. Biology syncs itself to rhythm. Beyond the solar system, many worlds may never know that rhythm at all. Tidal locking occurs when a planet's rotation period matches its orbital period, causing the same hemisphere to always face the star. Our moon is tidally locked to Earth, we see the same lunar face constantly. Many exoplanets, especially those close to small cool stars, are expected to become tidally locked over time. This is especially relevant for planets in the habitable zones of red dwarfs, because those zones sit close to the star. That leads to one of the strangest and most unsettling planetary possibilities: a world where one side is locked in permanent daylight and the other in endless night. This is not inherently fatal to habitability. That is important to say clearly. A tidally locked planet with a sufficient atmosphere or ocean could redistribute heat, potentially softening the temperature contrast between hemispheres. Climate models show that some such planets might still sustain temperate regions, especially around the so-called terminator, the line between day and night. But even the optimistic versions are alien in a deep way. There may be no sunrise in the ordinary sense. No shared morning crossing the planet. No global weather pattern built from rotating days. Only hemispheric climatic identity. One face of the world forever under the star. One face forever turned away. That changes everything. Atmospheric circulation, cloud formation, chemical stability, ocean transport, and surface habitability all become functions of permanent asymmetry. The day side may be desiccated, storm-driven, or scorched. The night side may accumulate cold traps or atmospheric collapse depending on pressure and heat transport. The habitable real estate, if any, may be narrow rather than planet-wide. Here the disturbing truth becomes more subtle. Tidal locking does not produce one universal horror. It produces fragility. Habitability, if present, may depend on finely balanced heat circulation, atmospheric density, volatile retention, stellar activity, and rotational history. The margin between survivable and catastrophic can become thin. And red dwarf stars complicate the story further. These stars are common, the most common in the galaxy, which means many potentially habitable zone exoplanets may orbit them. But red dwarfs can be flare-active, especially in their youth. Their close-in habitable zone planets may face intense radiation, atmospheric stripping, and space weather stresses. So the world's most abundant inhabitable zone statistics may also sit under conditions that challenge long-term surface stability. This is one of the recurring emotional traps in exoplanet science. A planet can be in the habitable zone and still be deeply hostile. Distance alone is not mercy. Tidal locking therefore occupies a strange place in the imagination. It is not as sensational as a lava world or as dramatic as a hot Jupiter. But it is perhaps more psychologically haunting because it takes a basic terrestrial rhythm, the alternation of light and dark, and turns it into a permanent wound in the planet's geometry. One side burned. One side frozen. And maybe, just maybe, a narrow seam where something could endure. That image captures much of what makes exoplanets disturbing. Not the certainty of doom, but the replacement of comfortable planetary assumptions with precarious alternatives. And if tidal locking unsettles by taking away sunrise, the next class of planets unsettles by taking away solid gentleness altogether. Some worlds do not merely host difficult weather. They host geology and atmosphere so extreme that the word planet begins to sound too mild for them. There are planets so close to their stars that rock is not a landscape. It is a phase transition. On these worlds, dayside temperatures can soar high enough to melt silicate rock, vaporize minerals, and create conditions in which the surface behaves less like terrain and more like an exposed industrial furnace at planetary scale. These are lava worlds, and they are among the most vivid reminders that rocky planet does not imply anything remotely Earth-like. Take ultra-short period planets, bodies that circle their stars in less than a day, sometimes in just hours. Their proximity subjects them to relentless irradiation and tidal forces. Some are stripped cores, perhaps the remnants of larger worlds that lost their outer envelopes. Some may host global magma oceans on their star-facing hemispheres. The distinction between surface and atmosphere can blur when the air itself contains vaporized rock. On certain worlds, winds may carry silicate material from the molten day side toward cooler regions, where it condenses and falls as mineral rain. On others, iron may exist as vapor in the atmosphere or condense under exotic thermal gradients. The phrase metal skies would sound like myth if spectroscopy had not begun teaching us how little mythology is needed. And then there is glass rain, one of the most famous exoplanet weather images for good reason. In some hot atmospheres, silicate particles may condense and be driven by fierce winds, effectively creating conditions in which glass-like material rains sideways at tremendous speed. This is not poetry overstating science. It is science discovering that poetry often lacks enough brutality. We should be disciplined here. Headlines can exaggerate. Glass rain is not a neat Earth-style shower of window shards. It is shorthand for silicate condensates moving within high-temperature atmospheric dynamics. But the underlying point remains: there are atmospheres and climates beyond the solar system whose chemistry and mechanics are not hostile merely by degree. They are hostile by category. Some planets likely have dayside temperatures capable of breaking molecules we think of as stable. Some may host nightside cloud decks of exotic minerals. Some have density profiles suggesting immense iron fractions. Some may be partially evaporating under stellar assault, trailing matter behind them like wounded embers. Some may be locked in such short-period orbits that their very existence feels temporary on cosmic timescales. These worlds matter scientifically because they reveal planetary physics under extreme boundary conditions. They help us test atmospheric models, tidal heating, escape processes, and planetary interior behavior. But they also matter emotionally because they widen the meaning of planets so far beyond habitability that human intuition loses its grip. A world can be rocky and still be unrecognizable as home. A world can have atmosphere and still be chemically hostile in every useful sense. A world can orbit predictably and still exist in permanent environmental catastrophe. That is part of what makes the exoplanet census disturbing. It does not merely show that some planets are bad. It shows that the parameter space of bad is vast and creative. And yet even these infernal worlds still share one comfort with Earth. They have stars. They have a primary source of light, heat, and anchor. The next category removes even that. It takes the idea of a planet and throws it into the interstellar dark. A planet without a star feels wrong at the level of instinct. In our experience, planets belong to systems. They orbit suns. They take light, seasons, and orientation from a central fire. Remove the star, and the word planet begins to sound homeless. But the universe may be full of such homelessness. Rogue planets, also called free-floating planets, are worlds not bound to any star, wandering through interstellar space. Some may have formed in planetary systems and then been ejected by gravitational interactions, migrations, or instabilities. Others, depending on how definitions are drawn, may have formed more like sub-brown dwarf objects in isolation. The line between planet and starless substellar object can become blurry here, but the broad reality is clear enough: not every world keeps a sun. This is one of the darkest discoveries exoplanet science has encouraged us to contemplate. Because a rogue planet is not merely far from warmth. It is severed from ordinary planetary meaning. No day in the usual sense. No year. No dawn. No habitable zone as typically conceived. No central star organizing climate and orbital identity. And yet even here the universe refuses to be simple. Some rogue planets may be frozen solid and lifeless. Others, if large enough, with thick atmospheres or internal heat, could in principle maintain subsurface oceans or deep insulated environments. There have even been speculative discussions of whether a rogue planet with a dense hydrogen atmosphere and internal geothermal heat might sustain some kind of habitable conditions without stellar input. That remains highly uncertain and model-dependent, not a license for easy optimism. Still, the existence or likely existence of rogue worlds changes the emotional map of the galaxy. It tells us that planet formation does not merely produce systems. It produces ejecta. It produces outcasts. It produces bodies whose history may include being born in a family and then flung into permanent exile. Imagine such a world. A sky with no sun. Perhaps a faint glow from distant stars, but no nearby stellar disk ever crossing the heavens. Surface temperatures plunged toward darkness unless atmosphere and interior heat conspire to resist it. A planet existing not as a member of a stable neighborhood but as a traveler through the deep cold between them. This is one of the strongest reasons the phrase deeply disturbing fits what lies beyond the solar system. The danger is not always violence. Sometimes it is ontological loneliness. Rogue planets teach us that not every world gets a home system. Some worlds are made to wander. They also remind us that planetary systems may be more dynamically ruthless than our quiet orbital diagrams imply. If enough gravitational chaos accumulates, not every planet survives in place. Some are scattered inward, some outward, some destroyed, some expelled. Stability, even when eventually achieved, may be purchased at the cost of lost worlds. And here again Earth's gentleness begins to feel less default than beneficiary. We are not a rogue planet. We are not a stripped core roasting under a giant star. We are not a gas giant skimming fire. We are not a tidally exiled hemisphere world or a silicate rain inferno. We are inside a system that held. That matters more the longer we look. But holding does not always mean simplicity. Many exoplanet systems are not chaotic in the sense of failure. They are structured, just structured in ways alien to ours. And that brings us to another disturbing lesson. The universe is capable not only of madness, but of order that feels wrong. When we think of disturbing planetary systems, we often picture obvious disaster. Planets colliding. Worlds burning. Moons torn apart. But some of the strangest systems are disturbing for the opposite reason. They hold together. Just not in a way we expected. Exoplanet surveys have revealed systems so compact and intricately arranged that they look less like scaled versions of our solar system and more like precision clockwork assembled under very different conditions. Multiplanet resonances, tightly packed orbital chains, and configurations with several planets inside the orbit of Mercury show that stability does not always mean spacious calm. It can also mean densely negotiated coexistence. The TRAPPIST-1 system is one of the most famous examples, 7 roughly Earth-sized planets orbiting a cool red dwarf in a compact arrangement, with several in or near resonant relationships. The entire system fits within a distance much smaller than Mercury's orbit around the Sun. This is not a solar system clone. It is a different style of planetary architecture altogether. Resonance is one of the key ideas here. When orbital periods lock into simple ratios, gravitational interactions can become structured rather than purely disruptive. Resonances can stabilize, synchronize, or sometimes destabilize systems depending on context. In our own solar system, resonances appear in various places, from moons to asteroid populations. But in exoplanetary systems, whole planetary families can be arranged in resonant patterns that suggest migration histories and delicate long-term balances. This is scientifically rich because it preserves clues about system formation. Planets likely formed in disks, migrated inward, interacted with gas, with one another, and with remnant bodies. Some were captured into resonant chains. Others broke free. Some systems survived packed and elegant. Others likely destroyed themselves or were sculpted by instability into the survivors we now observe. That last point matters. Every stable strange system may be the visible residue of earlier violence. Packed systems do not necessarily form where we see them in serene stillness. They may have undergone migration, damping, scattering, resonance capture, resonance breaking, atmospheric loss, and stellar irradiation. A system can look orderly and still have a traumatic history written into its present arrangement. This is another recurring theme in the exoplanet story. Survival should not be confused with innocence. A world can occupy a stable orbit now and still be the product of an earlier era of upheaval. The galaxy may contain many planets living in the aftermath of rearrangements more severe than anything our solar system is currently showing us. There are also systems with strongly eccentric or misaligned orbits, planets whose paths are not the near-circular, near-coplanar motions we grew up treating as typical. Some giant planets appear to have migrated through scattering events. Some orbit in ways tilted relative to the star's rotation. These are not trivial variations. They indicate that the processes shaping planetary systems can involve significant dynamical turbulence. The disturbing truth is that there may be many ways for a system to exist and relatively few that feel kind. Our solar system spacing and orbital calm are not the only version of order. But they may be a particularly life-friendly one. A system too dynamically unstable can disrupt long-term climates, bombard inner worlds, or prevent stable terrestrial histories from unfolding. A system too compact around an active star may offer multiple planets but saddle them with radiation and tidal stresses. A system with migrating giants may clear out the very region where gentle rocky worlds would otherwise persist. Once again, many planets does not mean many homes. And even when orbits cooperate, the air above those worlds may still be unimaginably hostile. Because if the geometry of a system disturbs us, the chemistry of alien skies can do something worse. It can make a world feel not merely foreign, but chemically indifferent to our existence. Atmospheres are where planets become intimate. A mass and orbit tell you what a world is doing. An atmosphere begins to tell you what it is like. And what we have begun to glimpse in alien atmospheres is not reassuring. Through transit spectroscopy and related techniques, astronomers can study the light that filters through a planet's atmosphere as it passes in front of its star, or the emitted and reflected signatures associated with the planet itself. This work is technically difficult, statistically delicate, and often entangled with noise, stellar contamination, and model uncertainty. But it has opened an extraordinary frontier. We are beginning to read the chemistry of worlds we cannot visit. What we find is a lesson in planetary cruelty. Some atmospheres are swollen, hot, and chemically dynamic under extreme irradiation. Some contain water vapor, yes, but not in the comforting Earth-like sense people often imagine. A hot steam atmosphere on a roasted giant or super-Earth is not a sign of beaches. It is a sign that water as a molecule can survive there in some form. Others show evidence for sodium, potassium, carbon-bearing molecules, hazes, clouds, or thermal inversions. Some are so hot that refractory materials, substances that on Earth belong to rock and mineral, become part of the atmospheric story. Clouds can be composed not of water droplets but of silicates or metal compounds. Pressure-temperature profiles can create chemistry unlike anything our biosphere has ever known. Even on cooler worlds, atmosphere is no guarantee of mercy. Dense hydrogen-helium envelopes can crush surface conditions. Carbon dioxide dominance can drive greenhouse extremes. Methane-rich or haze-rich skies can transform climate and photochemistry. Atmospheric loss under stellar activity can strip one world while leaving another swollen and insulated. Habitability lives not in the existence of air, but in a narrow set of atmospheric balances. There is something emotionally profound in this. From a distance, atmosphere sounds hopeful. It sounds like weather, clouds, sky, breath, circulation, maybe life. But exoplanets keep teaching the harsher lesson that atmosphere is just as likely to be an instrument of hostility as of habitability. The sky can be a weapon. A sky can smother, poison, irradiate, overheat, crush, or chemically isolate a surface from the possibility of complex life. A sky can become the whole reason a planet is unlivable. And because Earth's atmosphere is so ordinary to us, nitrogen, oxygen, water vapor, cloud cycles, pressure within a narrow human band, it is easy to forget how improbable that ordinary may be. To make matters more unsettling, our atmospheric interpretation tools are still developing. Spectra can be ambiguous. Clouds and hazes can hide lower layers. Stellar activity can contaminate signals. Retrieval models can produce multiple plausible atmospheric solutions. That means some headlines oversell certainty, while the deeper scientific reality is even more interesting. Alien skies are difficult enough to read that each robust detection is hard-won and each tentative claim requires discipline. This is especially true in the era of James Webb, which is extending our atmospheric reach and precision. Webb is not magically seeing aliens. It is doing something more valuable, giving us better constraints on the composition, structure, and thermal properties of distant worlds. And the better we get at this, the more the universe seems comfortable building atmospheres with no obligation to resemble anything life on Earth would enjoy. So the disturbing truth grows sharper. Beyond the solar system, we did not find empty silence. We found weather systems that make our idea of weather look provincial. But if atmosphere can intimidate us, habitability is the concept that humbles us. Because the more worlds we find, the clearer it becomes that being a planet is common. Being a good planet may not be. People often speak of habitability as if it were a checkbox. Right distance from the star. Liquid water possible. Case closed. But a habitable world is not a location. It is a long negotiation. A planet can begin in the habitable zone and still fail almost every deeper test that matters. It can lose its atmosphere. It can become tidally locked under an active star. It can suffer runaway greenhouse effects. It can be desiccated by early stellar luminosity. It can lack the geochemical cycling needed to stabilize climate over deep time. It can have excessive radiation. It can have crushing air, no magnetic shielding, unstable obliquity, or ocean conditions that frustrate the chemistry complex life would need. The habitable zone, useful as it is only the first filter. That is one of the most important lessons exoplanets have forced on us. The phrase Earth-like is dangerously easy to use and difficult to justify. Size similarity is not enough. Orbital distance is not enough. Even the presence of water, if confirmed, is not enough. A world can have water and still be a pressure-sealed abyss, a steam-wrapped furnace, or a chemically hostile ocean planet with little or no landrock cycling exposed to atmosphere. Earth's long-term habitability likely depends on a stack of conditions that are individually understandable and collectively unnerving. A stable star. A tolerable orbit. A survivable atmosphere. Carbon cycling. Plate tectonics perhaps, or at least some effective geochemical thermostat. A magnetic field may help. A moon may influence tides and rotational stability, though its exact importance is debated. Giant planets may have shaped impact environments, though the protective mythology around Jupiter is more nuanced than older popularizations suggested. None of this means Earth is miraculous. It means habitability is multivariate. And that has emotional consequences. Because if habitability is fragile, then the sheer number of exoplanets loses some of its naive comfort. Yes, there are many worlds. But the path from world to refuge may be narrow, and narrow in ways that are partly invisible at interstellar distance. A planet can pass the first tests and fail the deeper ones. A system can look promising in statistics and hostile in detail. A habitable zone can contain traps. This does not mean habitable worlds are rare in some final proven sense. We do not know that yet. But it does mean the universe has taught us caution. We should resist the temptation to convert planetary abundance into emotional certainty about life-friendly conditions. Some of the most intriguing planets in public imagination orbit red dwarfs, because those stars are common and their small size makes transiting planets easier to study. Yet these same stars can produce energetic flares, intense early luminosity phases, and tidal locking pressures that complicate the story. A planet in the habitable zone of such a star may still be habitable, but it may live on a knife edge of atmospheric retention and climate stability. Even ocean worlds, often imagined as romantic, carry ambiguity. Too much global water may actually hinder certain stabilizing geochemical interactions if the ocean is too deep and high-pressure ice separates liquid water from the rocky mantle. A world covered in water is not automatically Earth with more sea. It may be a radically different planetary system. This is why habitability should be treated less like a label and more like a treaty. A treaty between star, orbit, atmosphere, geology, chemistry, time, and luck. And treaties fail. The disturbing truth, then, is not that the galaxy lacks planets. It is that the conversion rate from planets to long-term homes may be lower and stranger than the optimistic imagination hoped. Still, finding many difficult worlds does not prove homes are rare. It only forces us to separate two ideas the public keeps blending. Many planets. Many homes. They are not the same claim. This may be the most important distinction in the entire exoplanet story. A planet is a category of object. A home is a category of outcome. Nature makes the first abundantly. The second may require an unusual convergence. It is emotionally easy to treat the discovery of thousands of exoplanets as if it were already halfway to the discovery of thousands of Earths. After all, if planets are everywhere, then Earth-like conditions must be everywhere too. But that inference is not licensed by the data. What the data actually show is a universe exuberant in world building and indifferent to whether those worlds satisfy our emotional needs. Think about what counts as a home from a biological and civilizational perspective. Long-term stability. Surface conditions neither sterilizingly hot nor globally frozen. A chemistry that permits complexity. An atmosphere that protects more than it punishes. Energy flows rich enough for life but not so violent they strip the world bare. Time, a great deal of time, for biology to evolve and for complexity to persist. That is a much narrower target than planet exists. And exoplanet science keeps emphasizing this narrowing effect. The more planets we discover, the more obvious it becomes that the universe fills planetary parameter space with ease. Massive worlds, puffy worlds, ultra-hot worlds, compact system worlds, stripped worlds, volatile worlds, isolated worlds, yes. But every new category also teaches us how many ways there are to be non-home. This is why the deeply disturbing element of the exoplanet revolution is not scarcity, but contrast. We look outward and see not emptiness, but a demonstration of how many environmental pathways miss the conditions we depend on. Earth begins to look less like the standard product of star systems and more like one successful route through a hostile combinatorial landscape. That does not mean Earth is unique. It means Earth should not be emotionally taken for granted. There is another layer here too. A world can be physically habitable in some technical sense and still not be an easy home. Surface gravity might be punishing. Climate variation might be extreme. Biospheres, if they exist, may remain microbial. Civilizational development may depend on contingencies beyond bare habitability. We should not lazily collapse some liquid water possible into another Earth waiting for us. This matters culturally because exoplanets carry an enormous burden of hope. They have become repositories for future escape, future contact, future humility, and future consolation. People want them to prove we are not alone, or that if we ruin this world, another waits. But science is not obligated to support our psychological backups. What we found beyond the solar system was not a line of spare homes queued for occupancy. We found possibility distributed across hostility. And yet the story remains open. There may indeed be many habitable worlds. There may be many inhabited ones. Perhaps even many intelligent ones. The point is not pessimism. The point is discipline. The existence of many planets cannot bear all the emotional weight people keep loading onto it. This is especially important when the conversation turns to life. Because once biosignatures enter the public imagination, hope becomes dangerous. And hope, in exoplanet science, must be handled with as much care as fear. Few topics in astronomy are as capable of distorting public language as alien life. A tentative molecule becomes a hint of aliens. An atmospheric anomaly becomes the strongest evidence yet. A planet in the habitable zone becomes Earth 2.0. The headline runs ahead. The caveats arrive later, if at all. This is understandable. The question of life elsewhere is one of the oldest and most emotionally explosive scientific questions we have. But that is exactly why caution matters. A biosignature is not simply any molecule associated with life on Earth. It is a potential sign that some atmospheric, surface, or chemical feature may be better explained by biology than by abiotic processes. The word potential is doing enormous work there. Oxygen, methane, ozone, combinations out of equilibrium, all can be interesting. But interpretation depends on stellar context, planetary history, geochemistry, photochemistry, atmospheric escape, false positives, and observational uncertainty. In other words, life detection at interstellar distance is likely to be one of the hardest inferential tasks in science. We are not sampling soil. We are not sending landers. We are often reading a tiny spectral fingerprint from a planet drowned in starlight. Even with powerful telescopes, ambiguities remain brutal. A molecule that on Earth strongly suggests life may arise abiotically under another star, in another atmospheric regime, or after a different evolutionary history. Clouds can hide relevant layers. Instrumental limits can blur distinctions. Retrieval models can overfit. Stellar contamination can mimic planetary signals. This does not mean biosignature searches are hopeless. It means they require patience, cross-checking, and a willingness to live with uncertainty. And this uncertainty itself is part of what makes the exoplanet frontier disturbing. We may be entering an era where tantalizing signs appear before decisive proof. Enough to inflame imagination. Not enough to satisfy rigor. That can produce a kind of scientific haunting, a long sequence of almosts. A planet with possible atmospheric hints. A world with a tempting radius and temperature. A spectrum that invites a life-friendly interpretation. Then revised analysis. Then caution. Then maybe later, another target. The public often experiences this as disappointment. But the deeper lesson is that life-friendly interpretation is hard precisely because the universe is chemically creative. There are many ways for a world to look interesting without being alive. Many ways to mimic promise. That brings us back to the central thesis of this documentary. The disturbing truth beyond the solar system is not merely that many worlds are hostile. It is that even the hopeful worlds are embedded in a landscape of ambiguity. The cosmos does not hand us easy homes or easy confirmations. It gives us gradients of possibility tangled with harshness. And yet we keep looking, because ambiguity is not futility. It is the honest cost of distance. Future telescopes, improved atmospheric models, multi-wavelength observations, and careful comparative planetology may eventually sharpen the picture dramatically. We may identify strong biosignature candidates. We may even one day assemble a persuasive case for life elsewhere through accumulated evidence. But if that happens, it will not be because hope won. It will be because discipline endured longer than desire. That is what science owes this question. And before we go further into the emotional meaning of all this, we need one section of explicit clarity. Because exoplanet science is rich with real findings, suggestive patterns, and speculative overreach, and if we blur those categories, we misunderstand the entire frontier. This is where we slow down and sort the darkness. Not to make the universe smaller. To keep it honest. #### What is established? It is established that planets around other stars are common. The galaxy is not sparsely furnished with worlds. Planet formation appears to be a widespread consequence of star formation. It is established that exoplanetary systems display a remarkable diversity of architectures, sizes, and orbital configurations. Hot Jupiters are real. Compact multiplanet systems are real. Super-Earths and mini-Neptunes are common classes in the observed census. Ultra-short-period planets exist. Tidally locked close-in planets are likely widespread, especially around small stars. It is established that many exoplanets occupy temperature and irradiation regimes with no Earth-like analog. Some worlds are likely lava-covered or intensely irradiated. Some giant planets have extreme atmospheric properties. Some systems are far more compact than ours. It is also established that atmospheric characterization of some exoplanets is possible and advancing rapidly, though the easiest targets remain biased toward large or strongly irradiated worlds. It is well supported that the solar system is not the only way to build a planetary system. What is strongly suggestive? It is strongly suggestive that our solar system may be less typical than earlier intuition assumed, particularly in lacking close-in super-Earths and mini-Neptunes and in maintaining its present broad architecture. It is strongly suggestive that planetary migration has played a major role in shaping many systems. It is strongly suggestive that habitability is more fragile and multivariable than simple habitable zone language implies. It is strongly suggestive that many planets in habitable zones around common stars may face major complications from stellar activity, tidal locking, atmosphere loss, or geochemical constraints. It is strongly suggestive that the universe produces many more ways to miss Earth-like stability than to approximate it. What remains uncertain or speculative? The exact frequency of truly Earth-like planets with long-term stable surface conditions remains uncertain. The prevalence of inhabited planets is unknown. Claims of biosignatures remain preliminary and contested in most publicized cases. The detailed interior structure of many planet classes, ocean worlds, stripped cores, volatile-rich super-Earths, often remains model-dependent. The abundance and life-hosting potential of rogue planets remain highly uncertain. Even when a planet is called Earth-sized, temperate, or potentially habitable, those are not conclusions about livability in the human or even biological sense. They are starting points for deeper analysis. What is overreach? Saying astronomy has found another Earth whenever it finds a rocky planet in a habitable zone. Treating every atmospheric molecule as a sign of biology. Assuming that because planets are abundant, life or intelligence must therefore be abundant. Assuming the opposite with equal certainty. Treating exoplanet discovery as proof that our world is ordinary in all the ways that matter most. Reality is subtler. What lies beyond the solar system is not a simple argument for optimism or pessimism. It is a rebuke to laziness. The galaxy is full of worlds, yes. But the relationship between worlds and homes, between homes and life, between life and complexity, and between complexity and intelligence remains unresolved. That unresolved state is not a weakness of astronomy. It is the integrity of astronomy. And now that we have drawn the lines properly, we can return to the emotional center of the story. Because all of this data does something to the human imagination. It changes how the galaxy feels. There is a difference between learning a fact and letting it reorganize your instincts. Exoplanets have crossed that line. It is one thing to know, abstractly, that the universe is vast and strange. It is another to realize that the places beyond our solar system are not mostly quiet variations on the home we know, but a staggering inventory of environments in which ordinary human expectations fail. For generations, space fiction trained us to imagine alien worlds as extensions of geography. Deserts, forests, ice planets, ocean planets, jungle moons, different, yes, but emotionally legible. Exoplanet science has made that imagination feel almost quaint. The real disturbance is not merely that other worlds look different. It is that planetary conditions can be governed by regimes so severe that the categories through which we emotionally understand landscape begin to collapse. A world can have weather and still be impossible. A world can have an ocean and still be hostile. A world can have the right size and still be chemically inaccessible. A world can orbit in the habitable zone and still be punished by its star. This changes the emotional meaning of the sky. The ancient comfort of other worlds had always carried a quiet human projection. Somewhere out there, maybe the same experiment happened again under slightly different clouds. But the exoplanet census keeps pushing back. The universe may make worlds extravagantly, yet build them on terms that make Earth look less typical than we had hoped. That can produce a real psychological shock. Because many of our intuitions about cosmic life depend not only on abundance, but on familiarity. We do not just want many planets. We want many settings where complexity could plausibly persist long enough to matter. We want the galaxy to feel hospitable in structure, not merely populous in count. What we may have instead is a galaxy full of bad neighborhoods. Not bad in the moral sense. Bad in the environmental sense. Bad in the climatic sense. Bad in the long-duration stability sense. And the more clearly we see that, the more Earth's gentleness begins to look like a local achievement rather than a universal default. There is something lonely in that realization. Not because it proves loneliness, but because it strips away a form of casual cosmic reassurance. It tells us that life-friendly architecture may not emerge automatically whenever dust gathers around a star. It may require a sequence of contingencies that many systems fail to preserve. Still, the shock is not purely negative. It also deepens wonder. A universe full of hostile worlds is not empty of beauty. It is overflowing with experiment. Physics, chemistry, and gravity have written themselves into planetary forms far beyond what the pre-exoplanet imagination would have dared. That is awe-inducing. It is also unnerving, because it reminds us that the universe's creativity is not aimed at our comfort. The cosmos is not hostile in the human sense. It is indifferent in a more absolute one. It makes blazing giants, stripped cores, locked hemispheres, and orphan worlds with the same lawful indifference that it made Earth. That is what disturbs us most deeply. Not that the universe is cruel. That it is capable of producing our refuge without making refuge its primary style. And once that lands, a new emotional inversion takes place. Earth stops looking ordinary. It begins to look precious. We have a bad habit of understanding value only after comparison. For most of history, Earth was not precious in the exoplanet sense because it had no rivals. It was simply the place. The stage. The given. Even once astronomy taught us that we were not the center, Earth remained psychologically generic in one important respect: we still lacked a planetary census broad enough to appreciate how specific our environmental luck might be. That is changing. Exoplanets do not prove Earth is unique. They do something subtler and perhaps more important. They reveal how much had to go right for a world like this to remain kind. A star stable enough. An orbit temperate enough. An atmosphere balanced enough. A planet massive enough to hold air but not so massive it becomes another category of world entirely. Water, but not too much in the wrong form. Climate feedbacks that did not run away into Venusian extremity or Martian collapse. Time, vast time, during which the system remained permissive to complexity. Even our catastrophes, on the cosmic scale, have been survivable rather than terminal. Asteroid impacts, glaciations, extinctions, brutal, yes, but not annihilating the biosphere altogether. The Earth system has been dangerous without becoming permanently disqualifying. Exoplanets make that history feel less guaranteed. And this has an ethical as well as philosophical consequence. When people dream of other worlds, it is often with an undertone of replacement. Another place to go. Another Earth somewhere else. Another chance. But the more we learn, the more irresponsible that emotional laziness becomes. The universe may indeed contain many habitable worlds. But the current evidence does not entitle us to assume they are abundant, nearby, accessible, or suited to human life in any practical sense. Earth is not just home because we were born here. It may be home in a deeper astronomical sense, a rare and specific arrangement of gentleness inside a cosmos that often prefers extremes. That does not make us special in the old arrogant sense. It makes us accountable. A fragile world discovered in a universe of harsh alternatives becomes harder to treat as disposable. Exoplanet science, paradoxically, can make environmental responsibility on Earth feel more urgent, not less. The sky is no longer full of easy substitutes. It is full of reminders that most worlds do not forgive the way this one sometimes has. This is why the exoplanet revolution is not only about astronomy. It is about planetary humility. We once imagined that leaving Earth would mean finding countless cousins. What we are actually finding is a gallery of conditions that underline how carefully balanced our own world is. A second Earth may exist. Perhaps many do. But no telescope has yet granted us the right to behave as though refuge is cheap. And now, with all of that in place, the discoveries, the atmospheres, the rogue worlds, the compact systems, the harsh skies, the narrowed meaning of home, we can say what the disturbing truth really is. Not in fragments. All at once. Let us gather the pieces without softening them. We began with a hope that felt almost reasonable. If the universe contains many stars, then surely it contains many worlds, and if it contains many worlds, then surely worlds like ours cannot be so unusual. The first part was true. The second was easy. The third turned out to be far more difficult. What we found beyond the solar system is not a single terrifying object waiting in the dark. It is something more unsettling than that. It is a whole census of planetary possibilities that forces us to confront how violent, inventive, and indifferent world-building can be. Hot Jupiters hugging their stars in orbits our old models did not center. Super-Earths and mini-Neptunes filling a size class our own solar system conspicuously lacks. Tidally locked planets where dawn never moves. Lava worlds where rock becomes weather. Giant planets with atmospheres full of exotic chemistry. Compact resonant systems built on tight gravitational negotiations. Rogue planets wandering without suns. Potentially habitable worlds whose promise sits under layers of stellar activity, atmospheric uncertainty, and climatic fragility. This is not the universe we instinctively hoped for. Or rather, it is larger and stranger than hope first designed. The disturbing truth is not that alien worlds are rare. It is that alien worlds are abundant in ways that make Earth-like gentleness feel contingent. Beyond the solar system, we did not find a second Earth waiting politely for us. We found a catalog of cosmic bad neighborhoods. We found a universe very good at making planets and not obviously obligated to make homes. That sentence must be handled with care. It does not prove Earth is unique. It does not prove life is rare. It does not prove we are alone. The scientific frontier remains open. Better instruments will come. Better atmospheric analysis will come. Better statistical constraints, better models, perhaps one day even serious biosignature cases, all may arrive. But openness is not the same as reassurance. What the data already justify is a more mature emotional conclusion. A planet like Earth is not simply a generic pebble at the right distance from a star. It is a long-running environmental success inside a parameter space full of failure modes. Too hot. Too cold. Too dense. Too gaseous. Too irradiated. Too unstable. Too airless. Too smothered. Too tidal. Too violent. Too chemically alien. Too dynamically unlucky. Many planets. Many ways to miss. That is the haunting architecture of the exoplanet age. And perhaps the deepest philosophical shift lies here. Before exoplanets, Earth looked like the first example. After exoplanets, Earth increasingly looks like one successful answer to a much harsher question than we knew we were being asked. What kind of world can remain kind for billions of years? The universe, it seems, has many responses. Most are not kind. This is why what we found beyond the solar system feels deeply disturbing even when no single discovery is monstrous. The disturbance comes from contrast. The more the galaxy reveals its worlds, the more our own begins to stand out not as the center of creation, but as a delicate climate, chemical, and dynamical equilibrium we were foolish to treat as ordinary. And yet there is wonder here too. A universe full of bad neighborhoods is still a universe full of worlds. It is full of physical possibility. It is full of atmospheres, minerals, orbits, storms, histories, migrations, collisions, and climates more various than the old imagination allowed. The exoplanet revolution has made the cosmos more hostile in one sense, yes, but also more intellectually alive. It has shown that planet formation is not repetitive. It is exuberant. The galaxy is not repeating us in a lazy rhythm. It is improvising. That is beautiful. It is also cold. Because the improvisation is not for us. So what did we really find beyond the solar system? We found abundance without comfort. Diversity without guarantee. Hope, yes, but hope fenced by caution. We found that the universe can produce countless worlds while leaving the status of home unresolved and perhaps rare in ways that matter. That is why the final truth is not that we should despair. It is that we should grow up. We should stop confusing more planets with more mercy. We should stop treating every habitable zone world as a second Earth. We should stop using abundance as a substitute for understanding. And we should stop imagining that the cosmos owed us familiar architecture outside the only life-bearing world we know. The disturbing truth beyond the solar system is not that it proves we are alone. It is that it shows how narrow, fragile, and contingent the conditions of a world like ours may be. The galaxy may be crowded with planets. But a gentle planet is a more serious thing. And from this side of the discovery, under this atmosphere, on this old blue world with its forgiving sky, that may be one of the most unsettling and precious facts modern astronomy has given us.